Hello everybody. Now we are going to talk about the equilibrium relations in more details. So again, we knew from the previous video that it represents the relation between the compositions in two different phases: gas or liquid, gas or solid, or liquid and gas. And of the same species in the two phases in case of equilibrium, because we have different compositions, so the equilibrium is not as easy as it is in case of heat transfer. And we mentioned that this is a critical piece of information that we need to know, and it's a must. If we don't know this information, we will not know how far we are from the equilibrium. We will not know what is the driving force, how many stages we need for any mass transfer process. So it's very, very critical piece of information. Now, this information, this relation, can be got by two main methods. The first is experimentally. We do experiments, we get the concentrations that are in equilibrium, and then we have the equilibrium relation as tabulated data. The other method is from basic theories, from the thermodynamics, from physical chemistry. We can get these relations in form of equations. So the first method, which is experimental data, is it's very simple. We start with like something like this. This is a case of gas-liquid equilibrium. We have a species in gas and in a liquid, and it is available in the two phases, and we need to know what is the composition in the gas and in the liquid phase that are in equilibrium. So we start with let's say in one of these beakers we put liquid and we put gas. Let's say this gas contains ammonia, which will be diffusing into or transferring into the liquid phase. So this has a composition of ammonia. Let's say we have it as 5 mole percent. And this is what we start with pure water, and then we have another beaker that contains, let's say, 10 mole percent, 15 mole percent, and we do this experiment for many experiments, or for many compositions. So we start with initial compositions that are different, and then we leave them for a long time and do good mixing, and we keep the temperature constant, we keep the conditions constant, and we keep it for, let's say, a day or two or a week until we are sure that mass transfer is done and all the ammonia in the gas phase that can transfer in the liquid phase has already transferred. And then we have the two phases or the two compositions are in equilibrium: the concentration in the liquid phase and the partial pressure in the gas phase, which will be different from the initial composition that I started with. So it doesn't matter what is the original compositions, the final composition is the main output. This is what I am looking for. So the results can be put as tabulated data in forms of concentration versus partial pressure. So this is the concentration in the liquid phase and the partial pressure in the gas phase, and these each one of these beakers represent one data point in this table. So this is how we get the equilibrium data experimentally. This can be done for any other system. Let's say you have an adsorbent that is absorbing some species from a liquid phase. You do the same. You get many beakers. You put a known amount of the adsorbent, and you have liquid phase with a specific composition. You do perfect mixing. You let them going for a few days until mass transfer is done, and then you calculate or measure the composition after the experiment is done. So this is simply what we do for anything to get the equilibrium data experimentally. Once I have this data, I can plot them. As you see here, we have here the partial pressure on y-axis of species A, which is ammonia, and the concentration on the liquid on the x-axis, which is the concentration of ammonia in the liquid phase. And these are the experimental data that we got. So we can use this data as is, or we can do data fitting to get the equation that describes the relation between the partial pressure and the concentration. There are many things that we can do. One other thing that we need to know about the equilibrium relation, which is very, very important, is that the equilibrium relation is a relation between compositions in two different phases. It doesn't matter what are the units that I use. So this same system that I have here, which is the ammonia in air and in water, can be represented in terms, or the equilibrium relation can be represented in terms of mole fraction. So this is the same as this. It's exactly the same set of data, but I'm using or putting them in other units, in mole fraction in gas phase and mole fraction in liquid phase. And this is also an equilibrium relation. So I'm mentioning this because you have to keep in mind that the equilibrium relation doesn't have any restrictions regarding the units or the phases. So you can have it in gas liquid, you can have it in solid gas, solid liquid phases. It doesn't have any restrictions depending on the phases that you have in your system. Also, it doesn't have any restrictions regarding the units. You can have this as concentration, you can have this as partial pressure, you can have this as molar concentration, as mass concentration, as mole ratio, as mole fraction. It's fine as long as you are putting the units right or correctly, and you are using the equation properly. Then it doesn't matter. You can have it in any units. So this is how you can get the experimental or the equilibrium data experimentally. You can do the same or get the equilibrium data with another approach, which is using theories from like basic thermodynamic concepts, and this is something that is like a whole branch of thermodynamics, which is getting the equilibrium data between two phases or three phases. The equations are generally complex, especially if you have non-ideal systems, non-ideal gas or non-ideal liquids. The equations are really complex in order to describe these equations or the equilibrium between phases. But in case of ideal gases and ideal liquids, it might be easier. And again, I think this is one thing that you might have an idea about, which is the main part of this, or the starting point of the thermodynamic relations, is putting the chemical potential in the gas phase and in the liquid phase equal to each other. And the complex part is how to describe the chemical potential. For non-ideal systems, it's very, very complex, and it requires a lot of thermodynamic calculations, especially if you have more than one or two species in the mixture that you have. If you have like 4 or 5 species, then it's extremely complex. So you have to do these calculations by yourself if you want to get the relations based on the theoretical equations. But anyways, this is out of the scope of this course. And usually in these kind of systems, we can have the data either experimentally, or we can find them in like any reference or any paper that was published before. So we're not going to go into these details, but what we will discuss are very simple cases of gas-liquid equilibrium. We will go through a couple of simple relations that we can use in some special cases. The first is called Raoult's law. Raoult's law is a law that is relating the partial pressure of a species at the interface to its mole fraction in the liquid phase. So let's say I have a mixture of A, B, C, and D, and A has mole fraction of XA in the liquid phase. So the partial pressure of this species A at the interface, at the surface of the liquid phase, equal its mole fraction in the liquid phase multiplied by the saturation pressure. This is Raoult's law, and Raoult's law can apply for pure component, and this is like one thing that can confirm that this is true. If you have X equals 1, then the partial pressure at the surface is the saturation pressure, which is what we all know. So this is Raoult's law, which can be used for ideal liquids, and we can combine it with Dalton's law if we have an ideal gas. So if I have ideal liquid in contact with ideal gas, then the partial pressure of this species A equals the mole fraction multiplied by total pressure. Combining these two equations together, we can get this relation, which is YA multiplied by the total pressure equal XA multiplied by the saturation pressure. In case of having constant temperature, this is a linear relation between mole fraction, of course, and temperature and pressure. If you have constant temperature, then saturation pressure is constant. If you have constant pressure, then P is constant. So the relation between Y and X is a linear relation. And this is an equilibrium relation. is a relation between two mole fractions. So I'm representing the concentrations in terms of mole fractions, not in concentration or in partial pressure. So this is the first example of the relation that can be used in ideal gas, ideal liquid systems. There is another relation which is called Henry's law, and it's a very famous law, which is used in case of low concentrations in the liquid phase. So this is the ammonia water equilibrium relation that we saw before. So what Henry equation is doing is it's just focusing on this part of the curve. So this part at low concentrations in the liquid phase will have, or the relation would be almost linear. So this is what the Henry's law is about. It's saying that since it's a linear relation, I can focus only on this part in the low concentration region. If I am operating at this low concentration region, then I can operate using this straight line part here, and describe my equilibrium relation as a straight line relation. This is fine for this low concentrations, but if you go further or at higher concentration, you'd see that Henry's law is deviating a lot from the actual equilibrium data that we have. So this is not possible to use, or it's not right to use this relation at high concentration, so you can use it only at low concentration. So Henry's law is simply relating the partial pressure to the concentration in the bulk of the liquid, and this is the partial pressure in the bulk of the gas, and this is H, which is the Henry's constant. And of course the Henry's constant here will have units that are units of pressure divided by concentration. So this is very logical, and this is one thing that we mentioned before regarding the units that we cannot subtract concentration from pressure or vice versa. So we had to use another unit that will be multiplied by one of them to make the units or one parameter that will be multiplied by one of them to make the units homogeneous in both cases. So this is Henry's constant, which has units of pressure divided by concentration. So it's centimeter cube atmosphere per gram mole. If you multiply it by concentration, which is gram mole per centimeter cube, we'll end up with atmosphere. And this is a relation that, again, we said is used for low liquid phase concentrations, and we know that the concentration in the liquid phase equals the mole fraction multiplied by the total liquid concentration. So we can rewrite Henry's law in this form. So we have here H multiplied by Cl multiplied by XA. It's called HXXA. And this is again an equilibrium relation that relates the partial pressure to mole fraction. So it's here it was partial pressure to concentration, and this is partial pressure to mole fraction. And I as I said before, doesn't matter what the units are that we are using, but we have to have one of them describing the concentration in the gas phase, one in the liquid phase, and doesn't matter what is the unit that you are using. In the textbook, the authors put this as H as well, and they said that we call this as H. I feel that this is very confusing. It has different units. It said it has different values, so it's not logical to have them both in the same units. So or the same symbol. So I put H sub x here to distinguish between this and this. So if it's H sub x, and this is what I'm gonna be doing till the end of this of the course. So if I have H sub x, then it's gonna be multiplied by the mole fraction. And if I have an ideal gas, then I can apply Dalton's law also. So this equation can be rewritten as HCl multiplied by PL, which is M, which we call the equilibrium distribution coefficient. And again, this is the relation between mole fraction and mole fraction. So we can write Henry's law in different ways, depending on the units that we have. We can have it pressure versus concentration, pressure versus mole fraction versus mole fraction. They're all representing the same system. So there is one last thing that I want to share with you before we finish this part, which is examples of equilibrium relations. So we know already that there are many mass transfer processes that, as we discussed before, require different equilibrium relations. So here I'm gonna show you 3 cases of equilibrium relations that we see in actual mass transfer processes. One of them is in distillation, which is the equilibrium relation of y equals kx, and k is called equilibrium constant. K is a very important parameter in distillation. So it's important to know what is this K, and to know that this is the shape of the equilibrium relation in case of distillation. In case of absorption or stripping, we use the relation between, here it was mole fractions, here it's mole ratios, which is the YA divided by 1 minus YA. So this is mole ratio and this is mole ratio. And the reason we do this depends on the derivation of the equations that we use in order to make the solution easier. So we have the operating line or the mass balance equation written in terms of mole ratio. So we put the equilibrium relation also in terms of mole ratio. The third is in case of adsorption. There are many equilibrium relations in case of adsorption. I'm just mentioning one of them. And in adsorption, the equilibrium relation is called adsorption isotherms. So one of them is called Langmuir isotherm. And this Langmuir isotherm is a relation between QA, which is the solute loading, which is how many grams of the solute per grams of the adsorbent itself. So this is the concentration in the solid phase, and the partial pressure in the gas phase. We have here two parameters, K and Qm, that are part of this equilibrium relation. So the point I'm trying to make is that there is no specific form of the equilibrium relation. There are no specific units of the equilibrium relation. The equilibrium relation can take any shape depending on the system, depending on the two phases that we have, depending on the ideality versus non-ideality of the system. So you have to be flexible regarding the equilibrium relation. You have to know that it can take any shape depending on the system that you are dealing with. This is all that I want to mention for regarding the equilibrium relation. In the next video, we will talk about the mass transfer between phases and see how we can use the knowledge that we have regarding the mass transfer between two phases, and how we can apply it to different systems, and what are the models that we use to describe mass transfer between two phases. So I'll see you then, inshallah. Goodbye.